Hi, greetings of the day to you all. I am myself Ajay Patel. I am going to present my video on one of the interesting topic and it is inverse quadratic interpolation. Yes, it is true that it's not from mathematics only. Yes, it is from numerical analysis. Yes, now let's we start further. Before I start my presentation, I would like to show you my outline, which are the topics and which are the parts that I am going to present in front of you about this topic. Once again, my topic is inverse quadratic interpolation, and I am going to present 8 parts to explain my topic. In the first part, I would like to show you introduction and background, in which I will give some introduction information, introductory information and background information. After that, I will show you the formula and procedure in which I will demonstrate the last formula that we have to apply for this type of problems, and which is the perfect exactly the procedure that one should follow to get the solution of the problem by this method. After that, I will show you the advantages and disadvantages. uh, as we all know that if we are discussing any matter, there is always the positive and negative aspects of that particular matter. So I will also discuss the advantages and disadvantages of this method as well. After that, I will show not one but two examples for this method to explain you the clearly, and I hope you will get the clear idea about this method by these two examples. It's enough. And after that, in one example, I will show you the comparison of this method with the other methods, and the other methods that I am going to compare is bisection method, false position method, Newton method, and secant method. After that, I will show you MATLAB code for this type of method. At end, I will present my conclusion. So yeah, let's we start next in introduction and background. So what is this method particularly? In numerical analysis, the inverse quadratic interpolation method is a one type of root finding algorithm, meaning that it is an algorithm for solving equations of the form fx is equal to 0. The idea is to use the quadratic interpolation to approximate the inverse of f. This algorithm is rarely used on its own. But if we see the word algorithm that I had used in this one, so what is the type of algorithms? Then there are the different type of algorithms. It includes the bracketing methods, combination of methods, iterative methods, interpolation. So our interpolation is actually included in iterative methods, and actually our interpolation is one type of part of Brand's method, and Brand's method is a combination of methods. So this is how it works. Yes, so let's now see the formula. Actually, this inverse quadratic interpolation algorithm is defined by the recurrence relation. And if you will see the last formula for the new root estimate formula is xn plus 1 is equal to fn minus 1 into fn upon, in the first bracket, fn minus 2 minus fn minus 1 into second bracket fn minus 2 minus fn into xn minus 2 plus fn minus 2 into fn upon fn minus 1 minus fn minus 2 in the first bracket over, in the second bracket fn minus 1 minus fn into xn minus 1 plus fn minus 2 into fn minus 1 upon, in the first bracket, fn minus 2 into second bracket fn minus 1 into xn. Here we are going to use xn minus 2, xn minus 1 and xn are the three initial values for this method, and we are using fk is equal to fxk. So yeah, if you will see next procedure of this method. So as we are seeing in the other root finding methods, this numerical algorithm is for solving the non-linear equation. It is fx is equal to 0, and if we talk particularly this case, the function f has to be a function of one real variable. There is a perfect procedure to apply this method, and here let's we go further for that method. First of all, we have to select three non-points on the function to be solved with at least one point on each side of the x-axis. Second thing is it should be in such a way so that fit a quadratic curve to these 3 points, and find the root x of the quadratic curve in the range of interest, and then we have to find the value of y such that it corresponds to the value of x. Then we have to replace the furthest outlying of the 3 trial points with this new point, and once again let's see next. Once again, as we had taken the initial values xn minus 2, xn minus 1 and xn for this method, and to get the y values we substitute the x values into the function f, which results in yn minus 2 is equal to fxn minus 2, yn minus 1 is equal to fxn minus 1, and yn is equal to fxn respectively. And here, assuming that f has an inverse quadratic function g, then inverse of f x n minus 2 is equal to g y n minus 2. After that, f x n minus 1 is equal to g y minus 1, and so on, like f x n is equal to g y. And this process should actually done by computing a parabola that goes through these 3 given points, and by taking the intersection of the parabola with the x-axis as the new root estimate, and fitting the points with the parabola in y. And if we continue this process, at the end of the process we have to we will continue this whole process at the end until we will get the acceptable small error. So this is how this whole process will go on. We will see further advantages and disadvantages of this method. So first disadvantage is will not converge if initial values are not closer. Like if the 3 initial values chosen are very far from a root, then the method will not converge. Hence, when this equation converges at the nth iteration, then xn is the root of the given function. Second is it cannot compute complex roots because it will always cross the x-axis. Further, if we see the advantages, then the method can converge very quickly to the solution if the initial values are picked close enough to the solution. And second thing is this method is also one of the fastest method for computing a root, and for the reason it is widely used today. Yes, let's see further. Example 1. Determine the least positive root of fx is equal to minus 2x raised to 4 plus 2x cubed minus 16x squared minus 60x plus 100. So here let's first of all we will set this function at 0. So fx is equal to 0. So equation becomes minus 2x raised to 4 plus 2x cubed minus 16x squared minus 60x plus 100 is equal to 0. Now a better guess for initial approximation values can be made easily as seen from the graph. it is clearly seen that the least positive root lies on the interval 0 to 2. So choosing 3 arbitrary, that's the initial values, say x0, x1 and x2, like x0 is equal to 0, x1 is equal to 1 and x2 is equal to 2. Let's see further. And evaluating the function at these points, like for x0 is equal to 0, then fx0 is equal to 100, y0 is equal to 100, for x1 is equal to 1, then y1 is equal to 24. Let's see further. For x2 is equal to 2, then y2 is equal to minus 100. Thus we get the corresponding y values when we are substituting the x values. Let's see further. Now, to make sure we will have a convergence, substitute these initial values in polynomial interpolation with Lagrange basis function gy, like shown in the first picture of the left side. And plotting the graph, we can see in the graph gy will intersect exactly. So yes, we can continue. Let's see further. Now the next step is we have to compute x3. So by using equation 1, we had already seen further, we get x3 is equal to approximately 1.25 for 66893 or something, and yes, corresponding to that x value we can also get the y values, and we will keep repeating this procedure until acceptable small error. So we will see further. So yes, so at the end of repeating this process, I obtained solution approximately 1.240787111. Thus we can say that the least positive root of fx in the next slide is minus 2x is 1.240787111 at this end of this process. Yes, let's see further. So let's compare this method with the other methods. First start with the bisection method. So here you can see that in the bisection method we can get the answer after about 25 to 26 iterations. So in compare of this method, the bisection method is very slower. Let's see the other method, the false position, in the next slide. Yes, so false position, you can see that we can get the answer after 10 iterations. So it is not as slower as much bisection, but still it is slower than in a quadratic interpolation, because we got in after 3 to 4 iterations. Let's see further the Newton method in the next slide. Yes, so in the Newton method, yes, here we are getting the answer after only 4 iterations. So it is mostly same in this case. Let's see further for the another method. It's a second method. Yes, so second method, here we get the answer after 6 iterations. So it is quite faster than the bisection, but still slower than the inverse quadratic. So this is how the comparison with the other methods of inverse quadratic. Now let's see next slide for the example 2. Yes, here we are going to take fx is equal to x e raised to x minus cos x. Let's start by taking fx is equal to 0 and then following all the process for the example 1. After seeing the graph clearly, we can say that the least positive root of the function lies on the interval 0 to 1. And let's choose the 3 initial values, x0 is equal to 0, x1 is equal to 0.5 and x2 is equal to 1. And In the next step, we have to evaluating the function by putting these initial values. So let's we see in the next slide. Yes, so by putting x0 is equal to 0, we get y0 is equal to -1, x1 is equal to 0.5, we get y1, and then x2 is equal to 1, we get y2. So at the end of this process, we get the initial points are 0 to -1, 0.5 to -0.05, 322, 193, and 1 to 2.17797,952. So our next step is to just make sure we have a convergence. So substitute these initial values in polynomial interpolation with Lagrange basic functions UI. Plotting the graph, we can easily double check and make sure that it is intersecting. Here it is already. So we can go continue. Our next step is compute x3. So let's we see in the next slide. Yes, so after following the process as per example 1, we got x3 and y3, and then after that we got y3 is equal to 0.01606658. So the new point is 0.52301554 and 0.01606658. So if we will go to the next step, we can get all the iterations, and it is as per the next slide. Let's go in the next slide. Yes, so after following the process, I got all the iterations like this, and at the end of this process I got the least positive root, and it is approximately 0.51775736. Yes, so here is the answer. So this is how the example second. Now let's see the MATLAB code for this method in the next slide. Yes, so here it is a MATLAB code. We can use it for this method particularly, and this is how all the presentation. Now at the end of this presentation I am going to conclude some information. Yes, so in the conclusion I would like to say that here in this method the trouble is that polynomial interpolation requires the abscias, which is in this case are FA, FB and FC, to be distinct. We have no guarantee that they are, and it is happens. Yes, like in example, like if we try to compute root 2 using fx is equal to x square minus 2 and start with a is equal to -2, b is equal to 0, c is equal to 2, we are starting with fa is equal to fc, and the first step is undefined. If we start near this singular situation, say with a is equal to -2.001, b is equal to 0, c is equal to 1.399, so the next iterate is near x is equal to 500. So this is a problem. On other side, in working with this method is very efficient method.